Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on word embeddings. It's part of the course Analytic Methods for Lawyers, but I do believe that it can be enjoyed by a broader audience. What I'm going to do in this essay is explore an alternative method of word embedding called glove. And the idea is that the similarity of two words in the original text should match the similarity of the two words when you represent them as vectors in a reduced dimensional space. Those are the embeddings. And it's not really all that much different than algorithms we studied in dimension reduction, such as multidimensional scaling and TSNE. The similarity of the two words in the original text is going to be measured by cooccurrence, how frequently within some block of text do the two words appear together. And the similarity of the two words represented as vectors in a reduced dimensional space is measured by something equivalent to cosine similarity of the two vectors. We're basically looking at the angle between the two vectors. Now in practice, a neural network is constructed that trains synced embedded layers so that the difference between the original similarity and the cosine similarity is minimized insofar as it's possible. In the second part of this video, I'm going to show you how professionally created word embeddings can be used to find meaning in text. So, let's start with a look at glove. And I'm going to use the same data that I did in the prior video. We're going to bring in a bunch of Supreme Court cases from the 2020 term. I'm using a little different file because, to be honest, I noticed a little problem with the file I used in the prior video. Nothing fatal, I'm not going to redo it, but this is an improved version. It doesn't have duplications. All right, now, the other thing I noticed when I took a look at these opinions more closely is that there's a bunch of boilerplate in it that Justia had put into it, and that's perfectly fine, but we don't want it. So what I'm going to do is I'm going to use regular expressions, which we studied in an earlier video, to capture the material that starts Supreme Court of the United States in all caps and ends right before disclaimer official Supreme Court case law. So let's create that regex. And now we'll use string cases with that regex, and we'll take the capture and we'll output it. And remember, string cases produces a list. We only want the first item, and I'm only going to be looking at the first 5 cases here. And this is going to produce our corpus. It's an 83,489 character extravaganza, and that's what we'll be using. So let's break it up into sentences. This takes a moment using some artificial intelligence to try and break it up into 675 sentences. And then let's take each of those sentences and find the words in it using AI, and then put them all in lowercase. We're not going to worry about case sensitivity here. It's going to take a moment. And we're done. All right, so there's our Supreme Court cases. Now, what I want to do is to come up with a representation of the cooccurrences. And by cooccurrence, what I mean is that word A appears in the same context as word B. And if that happens, we sort of get a point for that cooccurrence. And if it happens again, well, that's another point. And if it happens a third time, that's 3 points for that cooccurrence. The way we're going to do this is we're going to write a function cooccur, which is going to scan through the sentence and figure out how many times each of the words appear with each other. This is code that I don't believe you need to fully understand. If you want to study it, you can. The delete cases, just so you know, is there so that the same word isn't considered a cooccurrence with itself. This code is probably one of the more inscrutable pieces of code I've written in this course, but what it's going to do ultimately is it's going to produce an association in which the keys are the cooccurrence words and the value is the number of times it occurs in the corpus. And I've tried to provide an explanation of it here in text. I'm not going to go through that in the video. I don't believe it's essential that you understand it. All right, let's actually run this on the law words. The law words are all of these words divvied up into sentences that we found in those Supreme Court opinions, and we'll call it WCO. It's going to take a moment to do this. It's not the world's simplest thing, but in just a moment, I'm going to pause and we'll come back. All right, well, that actually took 3 or 4 minutes, but we're back, and you can see that it did have to find 8 million possible pairs, so you can understand why it might take it a while. And most of them are zeros. It didn't find any combination of structure and years or structure and Zant. Did find supreme and 10. All right, so we've got our word co-occurrence representation, and let's just take a look how many times a certain number of co-occurrences is found in the text. All right, and so you can see most of the time it doesn't find anything, but there are some co-occurrences that 140,000 times that happen once, 28,000 that happen twice, etc. But what we want to do is we're really not that interested in this situation where the words don't co-occur. We do want some of them to figure out how similar words are. This is called negative sampling, but mostly we want to focus on co-occurrences that actually did occur. So what I'm going to do is I am going to group our WCO values here according to whether they're greater than 0. If they are greater than 0, then we'll keep them all. If they're 0, then I'm just going to take a sample of them that's equal to twice the number of occasions on which I did have an actual value. This is called negative sampling, as I mentioned, and we do need to do some of it to properly train our neural network, but we don't need 7.5 million examples of things that never happen. So I'm going to get our adjusted WCO, word co-occurrence, and we'll have that in just a moment. All right, we've got it. And the other thing, by the way, is I scrambled it all at the end because when we're going to feed this into our neural network, we don't want it to be in any particular order. Now let's construct our training data, and we're just going to take the keys of this association here and the values of our association here, 0, 0, 0, 0, 0, 2, 1, and we're going to turn this into an association in which the keys are word 1, word 2, and target. And the idea is that we're going to use the embeddings of word 1 and word 2, the two words that co-occurred, to try and basically predict the target. All right, let's construct our neural network to show you exactly how we're going to do that. Okay, I want you to remember the goal. We want embeddings such that the cosine similarity of the embedding of the two words is closely related to the frequency with which those two words co-occur. Now, if our embeddings are of dimension k, like, k might be 25 or 100, and we have n words, like maybe 2,500 or 2,800, that means we have k times n parameters to optimize. That's 70,000 parameters. Functions like n minimize are really not built to work in settings where there are 70,000 parameters. So we've seen, though, that neural networks are very, very flexible. So what we're going to do is we're going to make an initial guess at the parameters when we initialize our network. We're going to take a batch of words, compute the difference between the embeddings of their cosine similarities and their actual frequencies, or a function of their actual frequencies. Then we'll differentiate that difference with respect to all the parameters and move the parameters just a little bit in a direction opposite the gradient. And if we do this long enough and cleverly enough, we're going to find an embedding that minimizes the difference between the cosine similarities and the actual similarity as measured by co-occurrence frequency. So let's build our network. We are going to need to know what all the words are, so I'll call that all law words, and we're going to need to know how many of them there are. So there are 2,839 words in our dictionary. Let's look at our layers. We have two embedding layers, one for each of the words. They're all going to map down to 25. I'm going to use 25 as my vector size to represent the words. They're going to start life at 2,839 possibilities, and the weights are going to be shared between them. Remember, we discussed this in the prior video. We need to force the weights of both of these embedding layers to be the same so that we have a consistent theory of embedding. And the way we do that is we label the weights with the thing net array, and we call it, it doesn't have to be W, I guess I like W, or maybe that's a convention, but it does need to be the same thing. We're going to need a dot layer to take the dot product. The dot product is a way of basically measuring cosine similarity. We'll need a linear layer to transform the dot product, and then we're going to need to take our co-occurrence frequency, and the convention is to take the log of the co-occurrence frequency plus 1. Why plus 1? Because if you have a 0, then you'd be taking log of 0, and that's not really defined. Why log? That's a good question. The makers of glove recommend it. I take it because the fact that something co-occurs, 7,000 times, like of the, it's really, you're not adding that much information with the 6,999th occasion or the 7,000th occasion. And so log prevents us from exaggerating those situations. And we'll need a mean squared loss layer to compare the similarity of the co-occurrence frequency with the cosine similarity as computed by the transformation of the dot product. We've got our connectivity. We're going to have word 1 going to embed 1, word 2 going to embed 1. They'll both then get fed into the dot product layer. The dot product layer connects to the linear layer, which connects to the loss, and then the target data feeds into that log layer that does that little transform, which also feeds into the loss. So let's load these up into our kernel. And we're ready to build our net graph. We do need to encode the data, and we're going to build an encoder that's based on all the law words and turn that into a class. Word 2, same thing. Our target's a scalar, it's just a number. And we'll have a nice little picture of our network. When it's all done, there it is. Word 1 feeds into an embed layer, word 2 feeds into an embed layer, they get dotted together, they get transformed by a linear layer and sent in as one element of the mean squared loss layer. We take our target, that's the co-occurrence number, we feed it into something that computes the log of it plus 1. That value goes into the mean squared error layer, out pops a loss, and then in the process of training, we're going to try and minimize this loss, which in turn is going to require us to optimize the parameters of this linear layer, which in turn is going to require us to optimize the parameter of embed 2 and embed 1, and it has to do that in sync. And ultimately, all we're going to want is this little chunk of it here, and we're basically going to throw this out. So in some sense, this is just a trick to get the computer to figure out what's a useful embedding layer. All right, let's actually start our training, and I see that training is blue, never a good sign. And so it looks like way back here I forgot to evaluate this. So let's evaluate it. Don't think it'll take that long. Good. So here's what our data looks like. Here's all the word 1s. You'll notice there are numbers in there, all sorts of weird stuff that Wolfram thinks is a word. Here's word 2, and here are our target values. A lot of zeros, but then we've got 1s, 17s, 21s, etc. All right, and with that, it is time for training. And what I'll do is I'll start us off on the training, and then I'll let it go and pause the video so you don't have to watch every moment of it, but it won't actually take that long. All right, it's processing the input ports. It seems to be having no success, and then It starts to dive down. It's actually found something. And it is now fixing the linear layer, it's optimizing the embed layer so that we are getting the cosine similarity of the words to be closely related to the log of the co-occurrence frequency. All right, I'm going to pause the video and I'll come back when we're at the exciting conclusion of training. All right, almost done, 96%. You can see we've basically stabilized here. We're not making much progress at this point. 98, 99, and we are trained. There's our net train results object. Okay, so we can get our embeddings now. And the embeddings, remember, are just the weights of the embed layer of the network. So we'll use net extract, and we want the weights of the embed layer. You remember that comes out as that weird numeric array thing. So we'll take the normal of it. And there they are. That's the meaning of the Supreme Court cases. All right, there is a lot we can do once we have embeddings, but instead of using my own homebrewed embeddings, I think it would be helpful to shift to professional embeddings, people who spend hours, days on way more powerful computers with way more training data than I have and came up with some good embeddings. So we're going to use real GloVe. GloVe was developed at Stanford University. They trained it on Wikipedia data, something called GigaWord. It's got 400,000 possible tokens, not just 2,800. And then finally, if you do give it a word it's never seen before, it's just going to return all zeros. So the GloVe model, that embedding, is stored in the Wolfram Neural Network repository, which you can just Google and go visit online to see what's there. And the function to get it is called netModel. And this is 100-dimensional word vectors trained on tweets. And guess what? I have the wrong netModel for what I want. Let's plug in the right netModel. All right, let's load that up. I guess there's another version that's 100-dimensional that's trained on tweets, and it's downloading a lot of stuff. And there we go. We've got our embedding layer. All right. Just so we understand what's going on, let's take our GloVe 100 netModel, or our embedding layer, and apply it to the word law. And it's going to take a moment, but you can see that we get 100 numbers here that somehow represent the word law. What else can we do? We can get a list of all the words that it knows about, and that's contained in the input port, and the input port has various features to it. One of those are tokens. So let's grab those. All right, that's everything that it knows about. Sigarms, Katuna, Choreothosaurus, I think that's a dinosaur. And what else can we do? We're going to create an association that goes from the word to the GloVe 100 encoding of it. You'll notice I'm not taking all of the weights here. I'm skipping the last weight, and that's because the last weight is what you do when you encounter a word you've never seen before. But the list of words are all the words that it has seen before. So we'll call this association word to vec. All right, and now we can do something kind of interesting. We can form a nearest function. We've seen those before. And it's going to tell us, if we give it a word in the proper form, what it thinks the closest words are. So it's kind of a way of finding words that are similar. Not synonyms, but words that are similar. All right, we've got our nearest function. I'm always amazed how fast that nearest function executes. And now let's take the word butterfly, and we'll apply our nearest function to it. we'll get the 5 nearest words. If I'm asking for the 5 nearest, why do I put 6? Because the nearest word to the word butterfly is butterfly, so I'm not really interested in that. And that's what the rest is for, to get everything but the first element. And very interesting, it thinks, I was talking about swimming. So I guess that's what it got a lot more information on swimming than it did on lepidopteral thingies that fly. All right. And that's interesting because when I trained this before, I was using the tweet training corpus, and when it was the tweets training corpus, I promise you it was much more about butterflies that fly. All right, let's see what happens when we look at what it thinks purple means. And purple, it does understand that. It thinks it's a color, and so we see things that are color-like, including blue and red, which we all know from kindergarten make purple, or that's what we were told. So what about words whose meaning is ambiguous? What happens here? And this is an area in which GloVe is not as advanced as some of the most modern embeddings like Elmo and others that understand context better. So let's see what it makes of mouse. All right, and actually here it does, okay, we have trackball. I'm not sure what robots have to do with it. Chimpanzees does seem to me to be a bit of a stretch. But anyway, you can see that there is that second meaning that it's picking up. And you can also see, frankly, how important the training data is. And so if you ever were to encounter this in any sort of litigation context where proof was really important, you need to look very hard at what was used to train the embedding layer. And of course, I'm a little curious about lawyers, so let's see what words lawyers are. All right, attorney, lawyer, attorneys, judge, counsel, colleague, asked, defendant, argued, prosecutor. Those seem all rather positive, so good. Now, here's something we could do. We could look at the words that are in the neighborhood of lawyers and sort of get a picture of them in 2 dimensions. We're going to be using a function, feature space plot, which basically tries to reduce these things down to 2 dimensions. I'll be using our GloVe 100 thing as our feature extractor. And let's see what we get. All right, let's look at this and see if it makes sense. We have attorney, counsel, solicitor, attorney, lawyers, prosecutors, prosecution, defendant, defendants, plaintiff, plaintiffs. So it does seem to be organizing things. We've got businessman and banker here. I kind of get this. I think these are Supreme Court justices. That would be my guess. Justice Roberts and Justice Stevens. I don't know about Peterson. Wasn't there some scandalous case involving a Peterson? I don't know. All right, so that's what we've got, and they do make some sense. But here's a more fun thing we can do. We can work with analogies. Like a human, if I say dog is to puppy as cat is to, most reasonably smart people will come up with kitten. And if that's true, then the vector joining dog to puppy should resemble the vector joining cat to kitten. So let's see if that's true. Basically, here's what we're solving. I want to get cat out. And so we're going to say a minus b is equal to c minus d solve for c. That's a minus d plus d. So this is dog minus puppy plus kitten. I'm hoping we're going to get cat. When I did it on the other ones, we did real well. And there we go. The second thing is cat, and I'll take that. I will accept that. That's pretty good. What about near is to far, as those are opposites, as closed is to, and I'm hoping we might see open. Open, that's okay because that's closed. So I'm feeling like we did pretty well there. Strong is to weak as hate is to, and I think we should see love here. And we do get it. We get kind, passion, love. So, you know, it has not perfect human intelligence by any means. But it is remarkable that, these 25 numbers are arrayed in such a way that it can actually do some linguistic thinking. There was one more I wanted to see, which was football is to touchdown as soccer. This is not right. This should be as goal is to soccer or to some sport where we have goals. Let's see. Goal is to soccer and hockey. Look at that. It did very nice. Good job. All right. So, in this essay, I showed an alternative vehicle for generating word embeddings. It's not the last word on the topic, but trust me, these methods are easier to understand than some of the others. I've also shown you a few uses for word embedding, such as finding relationships among words and analogizing. In the next essays, we're going to look at more complex methods of generating word embeddings and how you can then do sort of the holy grail of this whole thing, which is language modeling, to actually generate human language.